Okay, so this first one is not on the worksheet. I wanted to review counters and how you can use counters. I have some stuff later on about Johnson counters and ring counters and what they're like, but this is just how you would make a counter from a regular 4-bit synchronous counter that has a specific count. And so you can assume your counter works, and so you'll have a counter, and it's however many bits it says it is, and your homework problem has a 4-bit one, but you'll see how to do it if I do just a 3-bit one. So I'm going to do a 3-bit one, and you'll see how to do it. So it has an enable, and then it'll have inputs. It'll have 3 inputs, and a synchronous counter is most likely going to be made from D flip-flops. That's why they're called D, but you don't have to worry about how it's made. And you have a load, and you have a clock, and you have your outputs, and you'll have as many outputs as you have inputs. And you'll also have something that says output carry. The counter in your homework says output carry. You don't actually have to have that. You can use this even without the output carry bit. But and that's probably not going to be used. No, it would not be used in your homework. This is if you have to string together more than one counter, like if you needed an 8-bit counter and you needed to put 2 4-bit counters together. And so one way to do that is if your counter has an extra pin on it that says it's time to go to the next counter, but there's a way to do it without doing that as well. What you would do is you would link I'll show you. So let's just look at this 3-bit counter. So a 3-bit counter would count, and you can assume the counter works correctly. You don't have to make the counter. You can assume it knows how to count. So this would be counting from 0 to 7. And so let's say I wanted to link 2 3-bit counters together. So I would have another 3-bit counter that up until my first 7 was all 0, 0, 0. This is just to show you for later. It has nothing to do with this problem. And what you would do is you would link your outputs from Q0, Q2, and Q3. You would make an AND gate. This is getting really annoying. I need to change OneNote so that it stops doing these automatic shapes. So that it links, so you get your outputs from Q0, Q1, Q2 and make an AND gate, and then you link that to the enable of the second counter. And so the second counter is only going to count when the first counter is at 1, 1, 1, 1. Because when it's at 1, 1, 1, 1, the AND will be true, and that will enable the second counter. And so when it's enabled, the next time it'll count up, and this one will just count normally. Normally, the normal count after 7 is go back to 0, and then the AND will be turned off, and then it'll just continue counting until it's ready, gets to 1, 1, 1, 1 again, and then it'll enable this one, which will count up. So that's what the output carry is about. But we're not actually going to be using that in this one, but we're going to be using a similar concept. Okay, so let's say we want to make a counter that counts from I actually think I had one like this in the handout, so we may skip that one. Counts from 0, 1, 1 to 1, 1, 0. So it says it's a parallel, it's a synchronous counter with load. So this is a 3-bit synchronous counter with parallel load. Now what parallel load means is that it loads everything all at once. And so serial means you take one in and you put one out, and you take one in and you put one out, one at a time. Parallel means you load them all at once. So that means that here we want it to start at 0, 1, 1, and we have to remember that when we write our numbers, when I write 0, 1, 1, this is Q0, this is Q1, this is Q2. So I would want 1 to go to D0, because that's Q0, 1 to go to D1, and 0 to go to D2. So if I'm reading top to bottom, it kind of looks backwards from what I have there, just because when we write numbers, we put the most significant bit first. When a computer writes numbers, it depends on its processor whether it puts the most significant or least significant bit first. We want this counter to always be enabled, so unlike the example I did just a minute ago where we had the enable be something else, it should always be enabled. So we'll put 1 into the enable. We'll put the clock here. And now let's see what the count looks like if I do 0, 1, 1, and then the next one would count 1, 0, 0, and then 1, 0, 1, and then 1, 1, 0, and that is the time when I want it to then go back to 0, 1, 1. So I want it to detect when Q2 is 1, Q1 is 1, and Q0 is 0. So sometimes I can do this by just doing an AND of the ones that are 1s, and in this case I can also do that because if I look at these numbers, here, the first time that both Q2 and Q1 are 1 are when I'm at the number where I want to stop. And so if I AND those two, that means I'm at the stopping place, and I link those to the load. And what that means is when this is 1, it's going to load, rather than counting, it's going to load those values that are on D0, D1, and D2. And so when it gets to when both of these are 1, it'll say, okay, I'm going to load 0, 1, 1, and it'll start over again. Okay, so now just for practice, I'm going to pause, or actually I'll stop the recording and save it. And while I'm doing that, I'd like y'all to design a 4-bit counter, or if you want to do your homework problem while I'm loading this, you can do that, or I can, yeah, okay, all right, so I'll do that.